All right, we're back for the afternoon session here on my old sheet. Data quality. First speaker, Andreas, is going to talk about the new multi-state soil moisture test bed.
Okay, thanks, Todd. I don't know how my talk stands against the cookies, but I'll do my best. I'm excited to share this new initiative about the multi-state soil moisture test beds. I need to acknowledge the co-PIs of this project. So Brianna Wyatt at Texas A&M, Tyson Auctioner at Oklahoma State, and also Jerry Brown is going to be presenting something about that today. And Mike Kosh here at the USDA ARS. We're also working with the folks at NRCS in the offices of Salina and Lincoln. And this is part of the Dynamic Soil Properties initiative from the NRCS. All the data that I will be showing today is available in the GitHub repository. Also, all the data logger programs are there. And there is also an interactive website in our page for our lab at K-State, where you can actually select the sensor and depth that you want, and you can actually plot all the data that we are collecting. So a little bit of a background about the work that we've been doing. About 7 years ago, we started working with the Kansas Mesonet, and we had lots of questions. The first one that we had to answer was, what is the Kansas Mesonet? So we tried to find some identity there. We wrote a little technical overview to document instruments, protocols, and the products that we have in the network. We then had another question. It was, where do we place the next station? So we have a network in place, and we didn't really have a good protocol for deciding where to place the next station. So we created a little geometric approach there to find the largest and monitor area in the state, and thus serves as the tentative location for guiding or contacting landowners in that region. The next question that we had is, if we are going to have some soil moisture sensors in the ground, we probably want to do something with that in the future. So, what are the soil physical properties? So we visited every single station, we collected undisturbed cores, we characterized the soil hydraulic, thermal, and chemical properties. And then that was another big endeavor, but now we have that. It's been published, and you can see that in Kansas, we are biased towards silty clay loam, silt loam soils, with very few stations in coarse texture soils. The other question that we had was, how accurate are our soil moisture sensors and our soil moisture measurements? So we decided to calibrate the sensors and develop a few models so that now we can provide not only the raw data, but also some guidance on how to use that raw data to make the most, the best use, using the most accurate observations that we can using calibration developed for Kansas soils. But we still have some unanswered questions. Is what sensors do we use? It seems that this one is the first one we should have answered, but we didn't have really any testbed to decide that. But there are other networks that are planning to install sensors, or maybe to change all their sensors. So this is still relevant. And then the other question is, how many sensors do we need, and at what depth do we need to install? At that time when we started, we didn't really know, so we adopted the layout of the SCAN network. But as you will see, maybe there are other alternatives. So the goal for this multi-state testbed was basically to develop a platform for calibrating, evaluating, and disseminating, existing and new soil moisture sensing technologies, from the prong in situ sensors to the Cosmos sensors that you saw yesterday, and pretty much any other technology that might be in the horizon. Some of the specific questions and aims is, some of the questions that remain unanswered, and also we want these. Is that me or?
That's back there.
Something about the fire alarm. It seems that he knows what is the next slide, pretty much. And so, we also want to develop, as we build this test bed, we want to document and make everything available for people to, to save time and to see maybe as part of the protocols of the metadata that we are building. So we have 13 sites now across, 4 states. You can see that most of them are in grassland and 1 or 2 maybe in riparian areas. We span a wide range of soils from clay loams, silty clay loams in Kansas to clay loams and silt loams in Oklahoma to sandy loams here in Beltsville and in Texas. And we are also spanning a wide range of climate conditions where we can test all these sensors. The 3 sites in Kansas, they are located in a field at the Consa Prairie Biological Station. Here you can see site 1 and 2 in grasslands, and then site 3 is in a riparian area. This is the winter view. And then typically in late February, early spring, there is a fire. We burn the pasture, and after that, we get this nice verdant canopy. And like Brianna was saying, things change quite dramatically sometimes from the winter to the spring and summer. These are the sensors that we decided to select. These are mostly used for research, and this was the starting point. We have a set of prong sensors and then a set of multi-sensor profile level sensors as well. If you were yesterday in the field, I think these are more or less the same that Mike showed in the field. The installation followed the same guidelines that we covered yesterday. We selected the site. We excavated a small trench. We kept all the soil organized in layers so that we can put it back in the same order. We laid all the sensors in the ground. We did all the cable organization. Then we proceeded to install, having a good control of the depth. Then we wire everything and we connected the laptop to make sure everything is working. You certainly don't want to pack that trench and something is then not working at the end. And then we put it back. And after 2 or 3 rainfall events, you can see that the site looks pretty much like the one at the beginning. There is just only one pole sticking up on the ground. Looking at some of the data, I will not cover everything. This is just some sample of what we have. You can go to that website and really explore any sensor and depth combination that you want. But these are the prong sensors, the TEROS 12, the Climate 315, the Hydra probe, the Theta probe, and the CS655. And this is for site 1 at 5 centimeters depth. You can see that the time series, they look all very similar, except that at the beginning. So usually after installing the station, you want to discard maybe the first month or 2. But after that, the time series look very similar. Clearly, there are, some of the sensors are measuring drier soil moisture. And I suspect that might be because of the volume of influence. The CS655 and the climate may be measuring a little closer to the soil surface. But I am not 100% sure. We really have about a year of data, and we still need to do quite a bit of lab and field work to validate these sensors. And that's the challenge. Which is the ground truth here. So we decided to go this summer, collect some samples for gravimetric soil moisture determination. We went when it was very wet after the rainfall event, and a few weeks ago when it was really dry. And those are the 2 markers that you can see right there and right there. We took triplicate samples around each site, so you can see very little variation. And that shows that the sensors are within the range that we determined using the gravimetric method. Now that's at 5. Let's see what happens at 40 with about 45% clay. It's a completely different picture. Okay, all of these lines are showing the volumetric water content as reported by the manufacturer. Now we know that for some of these sensors there are better equations, and so let's see. So the CS655, when you correct, it really decreases. You can see that the temporal dynamics are very similar. It's just that there is a bias there that needs to be accounted with some sort of soil-specific calibration. Now, one of the things we thought, well, maybe we made a mistake when we started the sensors. Maybe one of them is a little higher or lower than the other one. So can you think of any way that you can use to check if the sensors are at the same depth once they are buried in the soil? We decided to use a soil temperature. So if one is a little higher or closer to the surface, maybe it has a slightly different thermal regime. This is the line for all the sensors overlap. So that at least shows that most, the sensors are about the same depth. But I do acknowledge that sometimes, when you're in a grassland like that, sometimes you have a nice grass and then all of a sudden there is a fork or something growing there that it might, the roots might get into the sensor. So it's really hard to account for what the vegetation is doing. Another thing that we did is to try to define this issue of the sensor depths. So what we did is we decided to visit the testbed and a few other places around the testbed. We have lots of experimental plots with a wide range of soil conditions. So we took soil samples, undisturbed cores, up to 105 centimeters depth, and we sliced this long core into 5 centimeters segments. We then computed the storage for that. And then we selected only a few of them, which are equivalent to a specific sensor depth. So how well can you represent the entire profile if you only select a few of those 5 centimeter segments? In that case, we are assuming that the sensor, so there is no sensor in the ground. We are assuming that the gravimetric method is the sensor. So that means like a perfect sensor. And what you see here is on the y-axis is the soil depth with surfaces at the top. And then the volumetric water content, is in the x-axis. The black line represents the volumetric water content of that high or finely sliced profile. And the red line in this case is the representation of that profile soil moisture using the scan layout. So 5, 10, 20, 50, and 100 centimeters depth. You can see it's actually pretty good. Only in cases where there is a little bit of, like in soil, the core 3, where I remember, I think there was a winter wheat or something that had quite a bit of soil moisture extraction from this layer. So in this case, you will need another sensor to actually capture that. But of course, adding more sensors sometimes is easy to say and really hard to do. So what we did is basically compute the storage of that entire profile using the finely sliced core and then the selected cores. And we found that for the current layout, we ended up with about 10 millimeters of absolute error. And if we remove a sensor, let's say the one at 10 centimeters, which sometimes is controversial, like that one, then we end up with pretty much the same error. So it seems that, if you have a sensor at 5 and a sensor at 20, the sensor at 10 does not seem to add much value. The same happens when we tested the layout that we currently have in the Kansas Mesonet, which is 5, 10, 20, and 50. And then we removed the sensor at 10, and we ended up with a very similar absolute error for all the profiles. So this shows that maybe we can, and the good thing about this is that we actually can test any layout because we have the information for all the cores, so we can test this. Now, we don't have much data about forest lands or other land covers outside of Kansas. I think Marena is collecting a few sites. And so if you actually have this kind of data, let us know, and we will be more than happy to include it. Okay, well, this is the result of the hard work of most of my students that really help with field work. If you have any questions, I would be more than happy to answer. Feel free to visit the MOISST repository. If you are a grad student and you need to connect a sensor and you don't know where to get started, go to that page. We have some data logger programs and instructions for wiring. And if you're using the Cosmos, we just developed a new library for processing of all the data from neutron counts to volumetric water content. So feel free to check that website as well.
We have time for a question.
Thanks, Andres. I think that was very interesting. I have two questions and you can pick one. Do you plan to do this for all the other soils that you've installed this at? Because I'm curious if this 10 centimeter was specific to this particular soil series that you worked with, and other places that might look different will probably be a different sensor depth. And then I was curious why the Acclima and the CS655, which I thought should have done better, did not do as well.
The first question about if we are planning to repeat this in other soils, those 12 cores actually span a wide range of soils from, loamy sands to heavy clay loam soils. They're all in the same region, and, for, soybean, corn, and wheat, and grassland and riparian area. But certainly we need to account for soils from other parts. And so, yeah, if someone is willing to help us with that endeavor, even as 1 or 2 cores will make the whole difference. And then the other one about the Acclimas and the CS655, this is just, again, what I show is what we are getting from the data logger using manufacturer defaults. We know that that is not, what sometimes needs to be used for research. But it does show that, at least the good thing is that all of them show the same dynamic. We didn't see anything weird on that. And it's just about adjusting that bias. But without any ground truth, it's hard to know which one is the right sensor. So hopefully next year, I will actually have more lab calibration and more field validation to tell everyone, more or less what sensors we recommend.
Yeah, I have 100 questions. So really the first one is, what are you doing later? But you answered my question about the cores. I was wondering about the variability of conditions in terms of how soon after precipitation events, or I imagine not a lot of snow melt where you were, but because I didn't see a lot of dynamicism in the profile compared to a lot of profiles I've seen with continuous monitoring.
The site has quite a bit of variability, and mostly due to vegetation. After burning, everything is homogeneous, but after that, there are some plants growing here and there that could take water differently. I would say for each trench, the soil is fairly homogeneous, at least for each horizon, because we also try to keep the trench fairly short, so that we don't actually span a large area where things can get too variable. But other than that, I don't know. I think we need to take more samples. We have undisturbed samples to do so, water retention curves, and it will be nice to show some of that variability. But at least from the gravimetric samples that we collected, I was expecting actually a larger standard deviation, and you can see that it's actually pretty short. So,
If I can, I'll ask one more question. The variability between sensors in the earlier slides versus the one that I definitely saw was at 40 centimeters. I assume those were shallower. Do you think any of that could be attributable just to micro topography, changes in root density and everything, even on the scale of the trench that you put them in?
Yeah, micro topography could be an issue. We try to pack everything. Sometimes when you go to the field, you start finding, so it's important to go to the field a few times after the installation, because after it rains, sometimes the soil starts to settle and it may create little depressions where water will accumulate. And so that could be, and you can see that at the very beginning, but it seems to me that later on that the time series are fairly consistent, but I don't know why some of the sensors are measuring lower moisture content. That is something that I need to figure out. We computed the sensing volume for some of these sensors, and it tends to be fairly narrow. But when you install at 5 centimeters, even if you have 1 centimeter of erosion or 1.5, just because the soil settled, maybe we are losing a little bit of signal. I don't know. I wonder if we can go to the field and try to poke the sensor head with a little stick and then see if they are really at 5 centimeters, or maybe they are much shallower than what I think. That maybe we need to do that. I don't know how I will find the sensors, but that might be a good thing to do.
I have a question about the cores. How far away from the actual location of your sensors did you take your core? What are you comfortable with as far as the boundary condition that you have to be away so that you don't upset the location for the sensors when you do your coring?
Yeah, that's something that we had to define in the field. We are taking the samples at about 1.5 meters sorry, about 2 meters from the trench. 2 meters. So about 8 feet. So if we get too close, then we are going to leave a hole there for preferential flow that may affect future readings. And if we go too far, then we are not representing the sensor. So we had to find a middle point. To address that, we actually took triplicate cores at each time around that. And so that is, but that's what I was saying, that the variation is actually lower than what I was expecting. And so I'm pretty confident with that. But we didn't take a core exactly next to the sensor.
Well, thanks, Andreas. He'll be around all day, so definitely ask more questions. We'll all have more. Including the library.